Hello and welcome back to this course on advanced data visualization with me, Robert, and Observable. This is the third installment. We'll talk about interaction today, and I'll talk about facets as well. I've actually decided to bookend these a little bit more with like having data viz at the beginning and end, and then have a bit more of the other topics in between. So things are a little bit different in structure than I had initially planned. But we'll start with a bit of data viz with facets, then we'll talk about interaction, and then we'll end with tree maps and sunburst diagrams if we actually get to that. And also, on the plan initially, I had said that would cover the Simpsons paradox today, but I'm going to do this next time because I feel like it's a bit too many things that are crammed into one session here, and instead I think it fits better on Thursday. So that's the plan, to do it that way. And with that, I'm going to just jump right into it. And I hope people are joining on time because I don't want to do a lot of small talk at the beginning because I feel like that's just a waste of time. Because right now I need to find my window here to switch over to this view. So we're back in Observable. And I do need to talk a little bit about Observable here because there has been some confusion about where we are, what I'm doing here. So this is of course an Observable notebook that you're seeing, and this is also where I'm doing all of this work here. You will see a whole bunch of examples today that are using D3, but that's still within an Observable notebook. It was just the very first time I had a bunch of slides because there was a lot of theory that didn't really feel like it would fit into a notebook format. So I used Google Slides for that. But other than that, pretty much everything is on Observable here. So what I'm going to start with today is to start talking about facets, and facets are a really interesting way of thinking about data that ties in nicely with the grammar of graphics. And it's kind of interesting how I started talking about the grammar of graphics, and then a lot of the things that I'm showing as data viz examples aren't really things that can be captured very easily by the grammar of graphics the way it usually works, especially today's tree maps later, because hierarchical structures are really difficult to capture in that kind of format. But facets are a really good example of things that work really well in the grammar of graphics. It's almost like it was made for them because it actually was. All right, so we're looking at this data set here again as a table. This is the penguins data set that has these different species and that live on different islands. And then we have these measurements. So we have their column length and depth. If you don't remember, if you weren't here for the last time when I showed this whole column thing, but it's basically the beak of the penguin. And so it has a length at the top, and then the depth is basically the height or whatever, the diameter of the culmen, and that gives you a sense of the size of the animal, and then flipper length and body mass, kind of the same thing. So what I'm trying to do here, once I can find my window with my cheat sheet, is I'm going to build a little chart that is just going to be a scatter plot. So nothing exciting here. We'll just start with a simple scatter plot. And we'll use the chart cell for this. So I think last time I showed mostly code. So I was talking about plot code and how plot marks are mirroring the idea of the grammar of graphics, because plot uses the same terminology, using marks and composing them and using and being a grammar of graphics. But there is the grammar of graphics, which is the book, The Grammar of Graphics. But then there are many other grammars of graphics that all have a lot of things in common, but they're all different in how the details actually work. Okay, so with that, so here we have this feature that's called a chart cell, or this type of cell. Actually, let me show you one more thing before I do this. I'm gonna get rid of this. So on Observable, in a notebook, everything happens within what are called cells. And when you hover on the left here, you can open up this Add Cell menu, and that gives you a whole lot of options for things to add. A lot of this is based on either text or code. So we have JavaScript, because everything is based on JavaScript, or Markdown for text, or HTML for HTML. And HTML is also for interactive elements, which you'll see more of in a little bit. But also it has a few of these little suggestions here. So here you can just create a chart, and then that takes the data set, or the previous cell's value, which this is a cell 2, this interactive table here, and I can now make a chart from that. So I'm going to do this by just picking the column length and the column depth, because I just want to make a scatter plot. That's the main reason. And then I am going to color this by the island. So this way I get this chart that we've seen before. I showed that either last time or the first time, I forget. But basically, this is a chart. This is just a scatter plot. And the point of this is just to show you how to use the scatter plot with facets. So it's really not so much about this particular data set. But you can see, of course, that by coloring these, well, in this case, they're colored by the island, but if I were to color them by species, you can see that there's a pretty clear distinction here, and there's a reason why people measure these penguins by their column depth and length, because you can see that there's a clear kind of clustering here of these 3 different species. So you've got the Chentus, the chinstrap, and the Adelie. But I'm just going to follow my script here. So I'm going to go back to the island, which you can already kind of see that there's something happening here, which is that there seems to be a bit of a mixing up here. But then there's these 2 other islands here that are much more like homogeneous in their populations. Actually, I'm pointing at the wrong screen here. Sorry, this one here. And so, so again, this is just a scatter plot. But what you can do with this is you can break it down into facets. And so we have this faceting field here, and I can say, well, let's go by species here and make 3 different facets, 3 different columns in this case, because I'm breaking this down in the horizontal direction, in the X direction. And these facets now are different from the scatterplot matrix that I showed you last time, because, I separated this out because it was probably going to be confusing to do both at the same time, because it looks similar, but it's different in that what this now does is it basically applies a filter on each of these columns. So or in each of these facets. So each of these is now a specific species of penguin, and I'm going to show you this by just changing the color here actually to the species as well. So you can see that now the color is the same as the facets. There's only 1 color per facet because we're using the same thing. And you can see that this shows us the same kind of separation into these clusters here ranges of values for their different kind of measurements. And also you can see something here which is kind of interesting, that you can tell that on this blue island, Bisco, the other way around. So Chentus only live on Bisco Island because they're all blue. Chinstrap only live on Dream Island, which is the orange one. And then these Adelies live on all 3 because you can see all 3 colors in here. So because I'm coloring by a different dimension than I'm using for the faceting, I can now see this kind of additional dimension here. And I can do more than that. So basically what I'm doing with this is I'm filtering by 2 different I'm filtering by 1 dimension, which is the species, and then I'm coloring by the other, and so that way I can see what combinations there are. But I can take this one step further by also breaking this up by island vertically. And so now I've created this sort of matrix, but in this case it's not a matrix of all the different data dimensions against each other, but it's all the combinations of the species and island values. And so with this, you can actually already see that a bit more clearly, I guess, that what I just said earlier about how the different species live on different islands, because there is no data here for these islands here for these 2 species, but there is for all 3 on this one. This is a bit of an unusual case, of course, because usually in the typical kind of case, you would have data in all of them. So you would have the whole matrix here of all of these filled in and have data. But either way, you would probably see a distinction between them. So you would see that perhaps the animals on one island are different from the other. So for example, you can see this a little bit here with the on Dream Island. Well, actually, no, I keep mixing up which dimensions which, but you can see that on the same island, of course, these different species are different, obviously, because they are different species. And they don't seem to actually differ a whole lot between the islands. So the islands is the vertical distinction, right? So because when I'm not confusing myself, I can actually tell that they're the same ones. And another thing about this, doing it this way, is also that I can just like change things. Like I can add a little bit of a space on the right here because we had some of these labels overlap. I can make changes to the color scheme and so on. I can work with this much more as a visual thing, but then I can always turn this into a piece of JavaScript. So I can just say make JavaScript, and then we get the same exact plot, but now this is created by code. So if there are things that that I'm not able to do, then I in the chart cell I can always do this in JavaScript. And what you can also see here is that and I hope you can see this. Actually, I'm going to zoom in here a little bit. Is that you can see all the mappings here as well. So we have the X and Y mappings, and these are the same for all of the facets and all of the points. And then we have these FX and FY fields, which are the faceting fields. And this can be specified in different ways, but this is the sort of the easier way to do it by just adding it into the plot.dot call. So this is the dot mark that's drawing these dots. Also, and this is actually a thing I should have said earlier, what's important about facets is that not only that they are filtering, but also that they share axes. So I'll come back to this later when I talk about filtering versus highlighting, because I think this is a really important point. So the fact that there's empty space here is because the axes for all of these charts are the same across all of these all of the rows and columns. So every single chart here has the exact same vertical axis scale, meaning just the range of the values on that scale, and the same on the horizontal axis. And this is important because otherwise you wouldn't be able to compare them, because you wouldn't be able to tell that these have a higher depth but a lower length, versus these guys have a higher length but a lower depth, because the values are in the top left versus the bottom right. So you can see that distinction, and the empty space helps you see that distinction. And I'll come back to this in a little bit when I talk about the filtering versus highlighting thing. But of course, facets are not like limited to scatter plots. So I keep using the scatter plot because it's such a nice, easy way of sort of like mapping numbers, or mapping a data dimension to a visual representation. But I can also go and just say, well, let's just duplicate this guy here, I guess, and make a new chart based on this. And I'll just say, let's actually look at this as body mass, and just get rid of these, and maybe even this. And now I have, and maybe I'll change this to species being on this axis. And so now I get a histogram of body mass for these different species, and the faceting, and they're faceted by species. So if I don't do this, let's start here. So this is now, the only thing I'm mapping here right now is the body mass on the horizontal axis. And so that gives me a histogram by default, because that's really the only thing that can be done when I don't know anything else about about what's supposed to be mapped. So the observable here in the chart cell are trying to be smart about what you probably want to do. So if you don't have anything mapped on the vertical axis, it'll just show you frequency, meaning the count of values of rows essentially in your data set, and you can then say, well, and then you can specify more than that. But of course, if you don't, then this is what you get. So you get this histogram of all the body mass of all of these animals. But it might not be very useful because it's all of these kind of thrown together, and that's not necessarily very informative. So if I break this down by species, now I can see that there's a distinction. So clearly the Gen 2 are larger, or at least heavier, presumably also larger than the other two. And so faceting helps you see that because it breaks the data down. And again, it's sharing both of these axes. So if you have, so we can see that we have fewer chin strap overall, because this clearly is more total than this one here. So the vertical axis is the same, and the horizontal axis, of course, because otherwise that's why they are aligned. So you can see that more clearly. And so this is fascinating. It's not really a huge topic, but it's certainly a useful thing to do, and it's something that I think is fairly commonly done. We'll get back to it, I think, with the time data, temporal data. That's next Tuesday, I believe, a week from today. But it's a very useful thing to do, and it's a useful thing to think about when you're creating charts. Just looking at the chat here right now, just to see if there are any questions or comments. All right. So then I will talk about our next topic here, which is interaction. And I have a little thing prepared here for that. So interaction is something that's kind of a big topic, and I'm going to just touch on a few things that I think are important. And I bet some of you will have comments and other things that you think should be done. But I want to basically talk a bit about interaction examples, like things that you can do in interactive charts and why you do them. But also be a bit cautious about it, as I usually am, to say it's easy to overuse. And maybe I'll show you a few examples first, and then I'll talk about that. So here's the simplest type of interaction, which is a tooltip. And if you've already seen that with the earlier chart, because you get this default tooltip here in plot or in observable, well, using plot on observable. But what I've done here is I have this simple chart here of the cars data set. So we have this cars data from the 1970s and 80s that has the economy value here, which is miles per gallon, versus the, I'll zoom in here again, the power in horsepowers. And so we get a scatter plot. And the scatter plot, it gives you this overall, again, I just scatter plot. I feel like I'm overusing them a bit. But what's nice about it is it gives you this overall sense of the data. So we can look at two data dimensions here, and we can see this dependency between the two. So clearly, the higher you go in power, in horsepowers, the lower you are in economy, meaning your economy is worse in using miles per gallon. And if you go lower in horsepowers, you go up in economy. So that's a very kind of clear pattern here. Along here, and it's somewhat not linear, so we probably would want to try and do some scaling here, but we're not going to do that, or like transformations, but we're not going to do that. And then, but I might ask a question, like I might ask, well, what about this one? So this, and I'm already showing you this because you can see it, but basically this point here is an outlier. So it has much higher economy compared to all these other cars, because you have to look at this as straight down, right? So this is much higher than the next one, like around about here, right? So this one is kind of a neighbor, and this one is a neighbor, but this one does much better. So which one is that? And so I've created this very simple tooltip here that tells me which car that is, so which model that is. And so it's got the name of the model year, and then it has the horsepowers and miles per gallon values just shown as a tooltip. And the reason this is useful is because what people like to do is they want to put labels on charts and numerical labels, numbers, and that can be very distracting because you get all these numbers in your chart, and now you have all this clutter that really makes it hard to see the patterns, because if I had a whole bunch of numbers on here, that would get in the way of seeing the actual pattern of the data. But at the same time, people want to see numbers, and they want to know, well, what is this thing? Why is this different? Or like, which one's the highest horsepower car here in this data set? And so on. So you obviously want to know what these data points are. You don't want to look at it as just a distribution, but to be able to do, so you either can add that, or you can make it interactive, make it possible to see it as an interaction. And so this is where the tooltip comes in as a very simple but very useful interaction. So I think it's just something that we really want to make sure that you think about having, and that's why it's actually kind of a default by in the chart cell, where you just get that as something that just shows up. And then so yeah, that's tooltips. I don't think anybody's got any strong opinions on those. They're clearly useful. And then and I'll just show you very briefly how this works. So in plot, you can specify this. This is called the title field here. And the way this works is that this is a bit of JavaScript code here that, and if you haven't done JavaScript before, this might look a bit scary, but it's actually fairly simple. This basically just says we're going to, for every data point, we're going to call a function. And the function here says, take a parameter, we'll call it D, and turn it into this thing here. So this is an actual function. It doesn't have a return statement because it's sort of like implicit when you do this, when you don't have a full function body with like square, the curly braces around it. And then it uses something called string interpolation. I hope I'm not getting into the weeds too much here. It uses these backticks. And then in here, you can use variables. So we're getting in this variable D, and D has names, has properties. So I did show this last time, I think, but very briefly, this is the way this works for the penguin data. We have an array or a list of values of objects that contain the data, and then each of those objects have properties. And so the properties have names and values. And I can access that just like a normal JavaScript object here, and I can just say d.name to get the name field of the car. So that would be the Buick Regal Sport Coupe, whatever, Turbo. And then I can say, get me the year. And so the year is another field. And because these are 2-digit years, I just said 19 and then the year, because this is simply string operations here. So we'll just interpolating into the string. And then I can access these other fields here as well. So the power and the economy, and that then pieces together this string that has these fields in it. And when the field name has a space in it, or any kind of character that isn't, that would be a character that's also used in JavaScript, I have to use this different way of accessing that. So instead of d.year, like here for the year, because that's just a simple label or it's like a variable name, I have to use this array notation to access that variable, or that field value, I should say, this property of the object. I hope that was more clear than it was confusing, but that is how this is constructed. It's actually a lot easier when you actually do it. It's kind of these kind of things that when you explain them, they end up looking a lot more complicated than when you actually build this. I'm not going to build it though, because I think it's going to take too long. All right, so my next example, or my next topic here, is filtering, and I'm going to show this using this thing, which is called cross filter. This was actually done by Mike Bostock a while ago as a totally separate project from D3 and certainly not and certainly observable. This was a fair time before that. And so cross filter is a nice example of creating filters and having them impact each other. And it shows a few interesting things, I think, about how filtering works. So filtering is perhaps the most common interaction. So I've talked about tooltips, and tooltips are useful, but they're not exciting. Filtering is much more fun. So filtering essentially means we have these different charts here. You could think of this as a dashboard where we have about 250,000 flights here, flight records in this data set. And we have their time of day, the arrival delay. So this is interesting for a lot of people who travel. They want to know, well, when is there going to be more delay? The distance of the flight in miles, and then the date when this happened. And this is, I don't even know what 2001 apparently. So this is data from 2001. And you can get this data actually fairly easily. There's a whole bunch of data that you can get fairly easily. And so what you can do with this, and that was the interesting thing back then, was to be able to just scrub over or like drag over to create a filter. And that filter immediately filters everything on this page. So it filters all of these charts here, and it filters this list. And as I move this filter along here, you can see all of these charts responding. Actually, I'm going to make this a bit smaller just so you see them bounce around a bit more. So you can see how these filters, how the other charts respond, because the data is filtered for all of them. So the filtered data is global, and you can see that this says it's 10,408 values that have been filtered out. And if I move somewhere else, it's going to be, just looking for some different number here, so it's 9,987 values. And if I make this much smaller, it's going to be like a single day, then I'm going to have fewer flights, and I can move this around. And this is the filter this is the data set, the resulting data, the filtered data that's shown across all of these charts at the same time, which is why they respond like that. And so what I could do here, for example, is I could say, well, let's see if I select arrival delays and I go from 0, so this is 0 and then it's negative. So when you're early, it's a negative delay, and when you're late, it's a positive delay. If I select here and then scrub over this way, what happens to the other charts? And what's fun here is that if I'm just going to pick this here, you can see that there is some kind of pattern emerging here that might be because of the day of the week. But also, if I move this further over to the longer delays, we get this ramp in the time of day. And it's pretty amazing to see that, because you can see that as it gets later in the day, there's more delay quite clearly. So you get more of these flights, because also, and all of these are showing number of records, right? So all of this is number of records for each of these bins. And so you can explore this here by saying, well, if I go higher, what does this mean? And so as the higher and higher basically says that that's where later in the day. And of course, this crosses over into the early morning even. As you can see, this kind of correlation between longer delays and being later in the day. So flying later means it's more likely to be late. At least it was in 2001. I think it's probably still the case. And then as we go earlier, we can actually find, oh, sorry, not earlier, but if I do this here, if I select something here and say, let's pick early flights, and then we can see that this is, that the delay now is pretty much centered. Actually, there might be a little bit more in negative delay, meaning flights being early in the early hours of the day. And I'm assuming that this is local time for each of these flights. And what you can also do here is you can combine filters. So if I can say, and when I click, it just removes the filter. Yes. Okay. So we just posted the link to the notebook there, and this is also linked from there, of course. So all of these things that I'm showing here are linked from the notebook that I'm for today. So last thing here about filtering is that I can combine these filters. So let's say I will pick, just to pick February here, which starts about here, and then goes maybe here. And then within February, I can say, well, show me all of the high delays. Let's grab this and make it taller. And so this way you can see that there is a, well, you can see the values that are in this bins, which is not actually a whole lot. Let's make this a bit bigger. So now we can see which days had these like delays of at least 40 minutes, let's say. And so then we can see that here. And then I might even say, well, and let's do this only for, I don't know, short flights, because this might be more annoying when you have a short flights and it's delayed by 40 minutes. Then let's pick those. And so that way you end up filtering down by combining all of these filters, because every one of those acts on the total data set. So if it has to be in all of these three highlighted values here, highlighted field ranges, to be included in this list. And so you can actually see the list if you want to. You can look at the list of those flights. But I don't know if that's nearly as interesting, at least for us. I mean, if this is something, if you're managing those for an airline, this is probably much more interesting for you. But so the filtering does, I guess, what it says, which is it filters out the data. It removes the rest. In this case, it does leave in the context a little bit for those fields that are being filtered. So if I filter one field, let's do this one again, I can see the rest of the data in gray, and the stuff that I have included in the filter in blue. And then if I add another one, you can see that the gray bars also change. So it shows me the total amount that I'm filtering from. But this one here, for example, which doesn't have a filter, only shows the filtered data. So it doesn't, and so that's why it bounces around. So because otherwise it would actually show you gray bars in the back and sort of like the blue on top. So you would see how many there were. And so this is the downside of filtering, which is that you lose context. Like it's really hard to tell how many each of those days are in the bin or in the range of filters that I'm selecting, because I'm not seeing that here. So the filter, and actually it's the same, it's true even within the filtered values, because I'm not seeing how many there were before the filters were applied. So the gray only is shown for the parts outside. So filtering, because it fully removes all the other data, it also removes that context. So it can be helpful, like I just showed you earlier here, was that like this interaction here, this correlation between time of day and arrival and the delay value that I've picked. And if we could see day of the week here, we probably also see that certain days of the week are probably worse than others. But it's important to realize that's what's happening here. We're removing data, and that can be helpful because you might want to narrow something down. Like let's just pick this one here again. Shortish flights here, and we'll pick March. Let's see here. So this gives us a reasonably small list of values, and so now I can actually go through that list because maybe that's what I need to look at. So I do get the useful thing here, which is that I can narrow something down. Like maybe I'm interested in a certain product group, and I just want to see that or something else. But I have to know that that's actually what I want. Versus the other thing, which I want to show you now, which is highlighting, where you keep all of the values around, but show the ones that you're interested in a different way. So filtering this is a simple example that I'm actually using from the previous course that I built for that. So this is this is a filter on the cars data set again, so just to use that as an example, and I can change these two values here to filter by weight, but the weight by minute max. I can basically take a range of weights here that I want to look at, and what's happening here is that I get that the filter removes these points as you would expect because it's a filter. And in this case, I actually have the axis pin, so you can see what's missing. So you can basically see that once this outlier here disappears, so now I basically see that I'm in a smaller range of the values. So pinning axes can also be useful to create context because it gives you a sense of what else there is, at least in terms of range. But very often what people do, and what's sort of the default in most cases, is that you don't pin the axis, you scale it to the data that's left. And when you do that, you now get this effect where you basically zoom in on the data. So everything that's removed, so here I've got everything, and as I remove points, we're sort of zooming into the remaining value range. And that's helpful when that's what you want to do, because you're now seeing more detail, more range for those values that you have left. But it's problematic when it's not what you're after, or if you're trying to understand what's the context of my data, because now you've lost that information. And so instead, I can highlight here, and with the highlighting, you can now see what else is in the data. So the highlighted values are obviously highlighted in blue, and the remaining values that I filtered out are still there in gray. And so that gives me a way to sort of see how my selected data, my filtered data, fits into the total data set. And that may be useful because that's what I'm trying to actually understand. Is like, how do these cars like fit into whatever question I have, or how do different kind of products compare to each other? How do different populations of penguins compare to each other? And so for that, you need to then keep the other data around so that you can compare that. I feel like I'm over explaining this, but it's something that is very common, like, because usually the filtering is the easy interaction that you can add, and the thing that a lot of tools just give you very easily. But and so it's just done by default, but because it's just there, it's easy. But I feel like it needs to be kind of pointed out that you can also just highlight and keep all the data there, and that might be what you're after. But again, it depends very much on what you're trying to do. I'm just checking here if there are any questions or comments. And a related thing here, a related interaction, is called brushing and linking, or linking and brushing. I need to get my focus back here. I cannot switch. There we go. So I've showed you this before briefly, I think. So we talked about the scatterplot matrix before. And I just need to get sorry, this was not what I want. There we go. So in the scatterplot matrix, we get all these different dimensions of data mapped or brushed, or not, plotted against each other. And so we get this, in this case, this is again the cars data set. And so we can see all the combinations of values. And a common a common interaction here is called linking and brushing, or brushing is the interaction, I guess, and linking is the fact that they are linked between the charts. So I'm dragging over this, and I'm creating this selection box here, and that this box is a filter, basically. So this filters a range of values, but we're still seeing all the other points, as I was saying earlier. It's essentially a highlight, really, but it's called brushing because I don't know, for historical reasons. Actually, I don't actually know why it's called brushing, but you can, well, maybe you can see it because of the way I'm doing this here. So I'm kind of brushing over the values, and I think there are brushes that also apply a gradient. So right here, I have the color mapped to one of the data dimensions, and I can pick which one. But there are brushes where you actually get a color scale, a color range to brush over the values. But the point of this is that I can say, well, let's take economy and power, which is the same thing that we just looked at. But yeah, let's take something else. So let's do weight, perhaps weight versus cylinders. So if I take this one here, I'm making kind of a narrow selection here. This chart, I'm not sure how well you can see that, but I want to show more charts. I don't want to zoom in too much. We get these narrow strips here because we have the number of cylinders on the horizontal axis and the weight on the vertical axis, right? So I can now basically go through here and select different numbers of cylinders, and this is a bit hard to see with the color being a little bit too bright in the middle there. But you can see that the low values here at least are clearly on the bottom of many of these charts, partly also because, of course, here we have the vertical axis be mapped to the same thing, but you can also see it for some of the others. And then as I go up in the number of cylinders, you will see these numbers kind of move up because more cylinders pretty much correlates with everything else. So the horsepower, of course, the displacement is going to correlate. And so all of these things are pretty much pretty easily visible. But you can also do this on things that are more unusual shapes. So there's one here. This one here is much less correlated. So if I select just this range here, which is these like lower like colors, actually I should just like pick something more random here, then as I brush around this, I can see where those points are. And so this is really the power of the scatterplot matrix, because once you go beyond a small number of points, even here we have only like, I think it's like 300 points or so, or 400 data points. It's not a lot of data, but it's really hard to even see patterns in there with just that. But because you can brush, now this makes it much easier to understand or to explore where there might be patterns that you might be missing otherwise. So the interaction here is really what makes this useful and more more useful and more powerful, but also more engaging and memorable. So that's the other point, right? So if you interact with a data set yourself and you find something, you'll be much more you're much more likely to actually remember that and take something away from this from the fact that you did that, than if somebody just showed it to you. Which is also the downside. So I wanted to talk about this briefly too, is that if I just give you all the data like here, it's basically saying here, it's all the data. Do it whatever you want. I'm giving the viewer or the user perhaps more control, but I'm also saying, well, the onus is now on you. You have to do the work. You gotta go through this and explore. I'm not telling you about this in the data. I'm just giving you a tool to do this yourself. And that may be the right thing, but very often I think it's not really what people want. They want you to do, you as the database developer, as a database designer, to think about the data first and find the interesting bits and then show those. And so that needs to be much more boiled down to the things that are the critical findings and the interesting bits. And so just to show you this also on the parallel coordinates, because I'm not sure if I think I showed this last time, but just very briefly to show this, I can do the same. So this is the parallel coordinates here on the cars data as well. And I can brush over one of these axes. So let's do, this is all very highly correlated. I'll just brush over horsepower here. So again, I'm just dragging over the axis, and then this creates this little selection box. And then I can move through here and see how these maybe I should zoom out at least one step here. I can almost fit this on the screen here. So at the top we have economy, at the bottom we have the model year. Let's just ignore the model year. And now my filter box is gone, interestingly enough. Oh, okay. Well, anyway, so I think I had, which one did I? This one, right? So, or power maybe. Interesting. Well, okay, let's do some power again. I'm just confused why it seems to lose the selection when I rescale it. Anyway, but I can browse, I can brush over, and can I resize this? Yeah, so it makes it a little bit smaller, and so you can see how the other lines or the highlighted lines move across here, and so that gives you a sense perhaps of how these values correlate across multiple dimensions. So you can see that much more clearly here. And let's see if I can actually do a multiple selection here. Let's do one on here as well. Yeah. So now if I do multiple brushes, I get the intersection between them. So I only see those lines that are in both of these ranges. And so if I go somewhere over here, there won't be any more like here. And so now I've got an empty selection. And if I go here, I can find like high power, high weight. And maybe I'm trying to find high power and low weight. So I can just move this here and move this one down. And well, there's nothing down here, but I can find the lowest weight at that high power range, which would be these ones here. So this is a way to explore the data and to really get use out of the parallel coordinates, because the parallel coordinates, especially because they're also very difficult to trace individual points, especially when you have these categorical or like discrete values where all of the lines collapse into a point, and then so you can't tell where the lines go. Plus, it's really tedious to do it anyway. So using these brushes makes it possible to basically query the data right in the chart, because you're basically saying, is this value in this range, is this value in that range, and then it returns, or it just shows you those values in the chart. I think, let's see what else. Oh yeah, and then my last interaction. Whoops. Oh, did I not? I had one more example, but I will just open this up here. No. Oh, because it's the wrong link, perhaps. That's the reason. Yeah, it's the wrong link. Okay, let me just find the correct link here. Where is it? There we go. Oh, it's the wrong link. I'll skip this one. So this the one. Oh no, there it is. I think I have it. Yeah. Let's get rid of this. Sorry, this was all prepared, and now I'm kind of showing you how the sausage is made. But anyway, so this is the example of an index chart. And I talked about index charts in the first course, in the fundamentals. So what index charts are is they are, let me see if I can actually see what I'm doing on the screen here. So this is stock market data for a bunch of tech companies here. Obviously, so this is Apple, Amazon, Google, IBM, and Microsoft. And for some kinds of data, it's pretty common to compare those values to each other, but you don't care. But it's more about like how have they changed from a certain point in time. So stock market data is a good example, because if you buy stock, you don't really care so much what the absolute value is. You care about how that has changed from when you bought it. So has it gone up or gone down, but from when you bought, not from whatever, like, because you don't care about that. Same thing would be another example that I usually show is the Case-Shiller Home Price Index, which has these home prices measured relative to each other in different cities within the US. And that is actually already an index, because it's indexed to January 1st, 2000. But you can then say, well, I bought my house in 2016, and so now I want to see how has it changed from there. And so you can re-index to that value, to that date, and then say, this is now where I bought my house, and then has it gone up or has it gone down from there? Because again, I don't care so much about like the overall indices. I care about how much it has changed from for myself. And so this is the same idea here for stock market data. So these lines here are the different stocks, and I can pick a date. I don't know, April is again 2016 for some reason, but April 18, 2016 is my index date. And so now this is the one where all of these are collapsed to a point, basically. So all of their values are now treated as 1 in this case. And then everything from there going forward and going backward in time is shown as a multiple or a fraction, depending on how you think about it. But it's a multiple that can be more or less than 1 if it goes up or down. And so this way you can compare from that point. And so in this case, Amazon has gone up the most, and then there's Microsoft, and behind it I think is Apple, and then Google and IBM has gone down a bit. But if you start earlier, things look a bit different because IBM has actually gone down more. And well, actually it doesn't look all that different, I guess, but some of these times you will see like Microsoft and Google bad laid out and Apple being lower here, and then maybe, I don't know, at some point Apple's gonna be higher than this, or maybe this would be later in this data. But you can see how these lines kind of bounce around and change as we kind of pinch them down to one value at a particular date. And in this case, there's no control actually for the date. So it's neat because you can just mouse over here. But it's also a little bit problematic because it's much harder to pick a particular date that you care about. And so in this case, what you would probably want is have a date control here that lets you say, well, what is the actual date that I want to start at? So having the interaction be on the chart can be a good thing, but it can also be quite distracting and not necessarily always be that useful. All right, so that's interaction. And then the last few minutes, I want to talk about a couple of techniques, which you're now getting a preview of because I have too many things open here. Oops, where are we? Oh, there we go. Okay, so this is my little notebook here to keep sort of like all the notes together. Okay, that's an interesting question. So is there any underlying reason why you're using Tableau colors? Or it's just my impression about the shades? So it's certainly possible that these are Tableau colors because these colors have been sort of around for a while and they've been reused in D3 and in Plot and I'm not actually sure about Plot, but it's certainly in D3. They are being used. They're pretty common, popular. So Marine Stone designed those, I don't know, maybe in 2004, 2003, 2004 possibly. And they're just a really good color scheme. So it gets used a lot. But they're not necessarily always actually those colors. So it may be that the color scheme is a bit different, but it just looks like it. But yeah, it's true that those may very well be Tableau colors. I'm not going to pretend like they're necessarily different. They're just all over the place. Like you find them everywhere. They're sort of like Excel colors and Tableau colors. They're very popular colors. All right, so back to hierarchical data now. So tree maps are a technique that I want to talk about because it's fairly commonly used these days for part-to-whole relationships, and it's interesting to look at its sort of history a little bit and look at where hierarchical data comes from, and or the data visualization, I guess, comes from, and why the tree map is called a tree map. Because it might not be obvious when you're used to it basically just showing a selection of values that are all that don't really have much of a hierarchy. So here is a illustration of the idea. I'm not sure if this is the best illustration necessarily, but this is from a paper that I'll show you in a second. The idea here is that we have a hierarchical structure, and you can think of this as like the folder structure on a disk drive or something like that, where you have a root folder, a root directory, and then you have subdirectories, subfolders, and those can be broken down further and further and further. But you can always basically find your way to the root by just going up in a specific way. So this is called, that's why it's called a tree, because it has the there's only one way from a leaf or from any kind of node, these are called nodes, back up to to the root. And that's important because the other kind where you have more connections between nodes, those are then those are called graphs. So trees are specific graphs, but because they have this strict hierarchy, they're easy to deal with. They're actually a lot easier to deal with than graphs. Graphs are much harder to do database on because you have all these possible interconnections that make everything much more difficult. So there's a whole huge space of tree visualizations, which I'm not going to go into any kind of detail about. But what people have been wanting to do for a long time is, or had been wanting to do for a long time, is to show data about the nodes. So let's talk about this as a file system. So if I'm trying to free up space or understand how much space am I using on my hard drive, what I can do is I can take the sizes of all of these. Let's say these are files here, and these are files, and I can sum them up for each directory. So this G directory has these two taken together, and then these are the I directory, and then all of these together are this one, and then everything added up together is this one. And so what I can do now is I can take, and this is the idea behind the tree map, is I can take a rectangular space and divide that up in the same way as the subdirectories for each level. So to show you an example here, to make this a little bit clearer, and I want to use a different example. So let's go with this one. So this shows this fairly well, I think. All of these examples use the Flare Toolkit's sort of like file system, which is an early Flash toolkit that Jeff Hare built many years ago for data visualization. And the tree here, or the way this is broken down in this tree map, is that the whole thing. So if you look at the top left here, where it says Flare, so this here is the whole thing, the entirety of the tree. And so if I were to zoom out, why is it zooming in when I'm zooming out? You would then see the whole thing here now. But I'm gonna stay zoomed in here just to make it a bit easier to see. And so within Flare, we have these different subdirectories. And so there are things like viz. So there's Flare, and then there's Flare/viz. I hope you can see this tooltip here. So this, I don't know what to call this color. This kind of more reddish, as opposed to purple. So this more reddish color here is the viz subdirectory within Flare. And then operator, this orange one, is now, so this is this whole area here, is the operator subdirectory within viz. So you see Flare/viz/operator. So we're going down the levels of this tree, of this file system. And eventually we end up, and so in this case, we then go into layout, and then with that, we end up in these individual files. And so these are the what are called the leaves. So the last point on a tree is called a leaf. That's the metaphor. And these have sizes. So you can see sizes here, which I'm assuming are bytes. And so each of these is represented as a rectangle on the bottom level that is representing its size here. So this one is 2,700. So this is smaller than these, which are like 12,000. So and this is done as in the same well, by having the same, what's the word I'm looking for? A ratio, same ratio between area and value. So the value here is 2,700, and the value here is 12,000. So this is close to times 4. So this little one, the pie layout, is about a quarter the size of the radial tree layout. And so you get a sense of the different sizes of these individual files. And then if you go up a level, so layout here versus label, for example, you can see label is just this little bit here. Label is much smaller than layout because we're just adding up all those values, and then those become these directories. And you can do this across many levels. And so this is sort of like the initial idea of the tree map, is to represent hierarchical data by subdividing a space. And I'm not going to get to all of this, but in this example here, which is actually showing you the same data set, but it's harder to necessarily appreciate that because we're getting fewer of these labels. So this is more of the traditional style tree map because it actually shows you the labels here for these rectangles. But of course, these labels take up space. Technically, they're not really showing the areas in the correct way because the labels are taking up space that isn't part of the space that's allocated for sub values on each of these. This one here is a bit more of the now common way of doing things by having a layout that doesn't actually show you the subdivisions or the folders of the levels in between. It just shows you the bottom level of the leaves. So you can still see, like we just had earlier, the radial tree layout and the pie layout. We saw those earlier. And as I mouse over, you can see this sort of like hierarchy here, this sequence of values, but you're not seeing the levels as much. But you do kind of see them because you can look at these dividing lines here. So they're thicker between the higher levels and they get thinner as you go down the tree. But this is really hard to read. So the point of this is much less the tree and much more representing the values correctly. So this gives you more space for those values. And just for sort of a bit of history here, the original tree map looked more like this, which is called the slice and dice layout, where you go, in this case, you start horizontally. So the first one you look at, so this is Viz, so this gray color here is the first one that we take the space and we cut it into horizontal slices, or I guess vertical slices, but we're going horizontally across here. That's the first level. And then the second level, we now start doing this vertically. So now we go down this way and cut horizontally, but we're making them vertical slices. And then the next level, we do the same thing again horizontally and so on. And we switch every other level. And what this does, though, is it creates these very thin slices by necessity, because you just end up with just so much space that you're going to have to then subdivide. Like here, there's just a lot of files in this specific folder, and that's just, you just end up having very little space that you have to subdivide in a specific way. That's dictated by the algorithm here. And so the squarified layout, which I'm linking to all of the stuff from the write-up. The squarified tree map was developed in 2000, I think. Oh, and I forgot. So the original tree map is from 91, but the squarified layout is from 2000, and this really changed things a lot, because now there is an optimization step here that tries to keep these all as square as possible. That's why it's called the squarified tree map. And that has a huge impact on readability, because you can see, well, this has switched around, but all of these little files here next to my face are much more at least accessible, and you can compare them. Because the problem with the slice and dice is that because these are so thin and they are such a weird aspect ratio, it's really hard to compare these things to these, for example, because this is now longer, but it's also wider. But so how much more or less is this? Or like this one here compared to that one, or even to that one, because you basically have to make up for the height with the width, and that's really not something we can do very well. In fact, they're actually really bad at this. So squarified is easier because it's easier to compare things that are more similar in aspect ratio, and it also makes it easier just to label things, because now we've got labels here that are at least somewhat readable. Actually, they're fairly readable because they have very short names. But so the squarified tree map is really what people know today, but it also has taken out a lot of the structure, the hierarchy. And in fact, a lot of what people do today with tree maps is really to show essentially one level. So it's a part-to-whole relationship more than anything that's being shown in most tree maps these days. And that's because people prefer that to a pie chart, because pie charts have a bad rep. But it actually turns out that tree maps aren't better necessarily than pie charts, at least not for a small number of slices. But the tree map sort of like is considered the more acceptable representation of part-to-whole relationships. But that works for that, of course, because and you can read that, you can get a sense of what the value is. You can compare within the tree map a bit, and you can also compare part-to-whole, like how much is any one of those. So if those were products and like sales of products over time, or like for a quarter, you would then see what that value was. I'm running over a little bit here, so I'm going to skip over the other tree visualization that I wanted to talk about. I might cover this very briefly next time. but we'll talk about uncertainty in data next time on Thursday, and we'll talk about the Simpson's paradox as well. So I want to talk about a few more data-related, data-focused things then, and a bit of database again, of course, as well. So thanks very much for watching. If you have any questions, please post them in the Slack channel, and I will see you all on Thursday.